Okay guys, let's take a look at today's lesson. We're going to be working with functions of two variables. Basically, functions of two variables, if we graphed them, would give us a three-dimensional graph. An example of a function of three variables would be this formula for a perimeter of a rectangle. So, of two variables. The two variables here are length and width. We know that perimeter is a variable, but when they're talking about functions of two variables, they're really talking about these two, not this third one. Also, another example of functions of two variables would be in the three-dimensional coordinate plane, like z equals x plus y. That would be an example of two variables, functions of two variables. Now, I know you probably really want to graph these in three dimensions. We're not going to. If we were to graph them, it would be in three dimensions. So let's look at the perimeter formula. And this P equals 2L plus 2W, this would make this kind of three-dimensional graph. It would make a plane. And we're not going to graph the plane. What we're going to do is we're going to reduce it to two different ways to do it in two dimensions, to graph in two dimensions, is what we'll be working with. And so the two different ways are listed right here. We have the first technique would be to draw curves for various constant values of either W or L, one of these two variables. And we have an example of this, because this is probably the more complex thing we're going to be studying in this lesson, is actually graphing the function of two variables. That's kind of what is difficult in this lesson. So the second technique would be to draw curves for which the perimeter is constant. And so here's these two examples. Here's curves of constant width. Notice we have a W equals 1, 2, 3. We have perimeter here on the the y-axis, and then we have length. So that's one technique. The second technique would be constant perimeter. Perimeter is 4, 8, 12, and it gives us the values of L and W. So we do have three variables represented on there. So what's important is whatever curve that we draw, we need to label it. Otherwise, how would we know? How would we know this is when W equals 1 unless we put it here? Because there's no W on the graph at all. So we really do need to label each curve that we draw with whatever reference it has. Okay, so that's one of our goals for today. Another goal for today is to look at graphs of two variables and be able to read things off of them. So here's an example of one of them. So a pressure gradient force on the weather map, that's one example of a graph that's actually a three-dimensional graph. They've collapsed into two dimensions. So let's just kind of go through what all these things mean. Like the H is so here's our map right here. The H stands for a high pressure location, and the high pressure, if we go to the center of the high pressure location, it decreases on all sides. So right here at the center, from the center, the pressure is decreasing as it goes out. If we look at the L, which is a low pressure, the low pressure increases in all directions from the center. So if we go here where the L is, we know as we're going out from all directions, the pressure would be increasing. The contour lines are called isobars. They're lines of constant air pressure, and they have numbers by them. So this little bar has a number of 10, 12. These are these constant pressures right here. And then the strength of resultant wind is proportional to the isobar spacing. In other words, the less spacing, the closer the bars are together, the stronger the pressure gradient, or the strong so if this is close together, there's just some strong winds in here. This is farther apart and not as strong. So that would be a way to, the strength of the resultant wind is proportional to the isobar spacing. Okay, less spacing is stronger. All right, so that's an example of a three-dimensional concept put into a two-dimensional map that we will read also. Okay, so those are the two things that we're going to cover today. Let's go ahead and go to the next page where we work on the graphing. And we're just going to walk through this. So we have a volume of a cylinder as given by this formula. This is a function of two variables. The variables are R and H. And we're going to practice both techniques for graphing a three-dimensional figure in 2 dimensions. We're going to sketch the graphs of v versus r for these particular heights, and then we're going to sketch the graphs of h versus r for these volumes. Okay, so let's go back a little bit slower, one at a time. So this wording, v versus r, we may not be familiar with that. It's really telling us which variable to put on the y-axis and which variable to put on the x-axis. The v, the one they say first, goes on the y-axis. So that's what we're going to do. We'll put a v here and v versus r. So it's really important that you label the axes. We can't just take the implied x, y. That's not the way it's going to be. You need to label the axes of your graph so that we know which variable you are working with. So that is v, graphs of v versus r. Now we're going to do it for specific numbers, 1, 2, and 3. So I'm going to kind of walk you through that process. The first thing that I would do is to write it in a more formal form so that we just so that we know kind of how things are structured algebraically. So RH, okay, that's the order of our variables. V of RH equals pi r squared h. So what we're going to do is we're going to work on this first one, h equals 1. So v of r comma 1. And I put a 1 in for h, and then I get just pi r squared. Okay, and so we're going to graph that in just a minute. I'm going to generate all of the equations first, and then we'll graph them. For h equals 2, we would have v of r2. So let's see, that would be 2 pi r squared. And then for h equals 3, we have v of r3, which is, let's see, 3 pi r squared. Okay. On our axes, what I did is I labeled 3 r of 1, 2, and 3. And on the volume axis, I did in terms of pi. I did pi, and then 3 pi, and then 5 pi, 7 pi, and 9 pi. Okay. All right, so let's go to the h equals 1. Okay, we're going to work with this one. So when we're going to plot it on here. So when r is 1, v is pi. So that would put it right here. Now let's talk about when r is 0. If r is 0, we don't even have a figure, do we? So really, for reality purposes, that's not possible. It's not possible to have an r of 0, then we don't even have, volume. That doesn't make any sense. And likewise, we can't have a negative v or a negative r either, because that's not really realistic. It's not realistic to have negative r's and negative v's, so we don't graph them. All right, so we did r of 1. Let's do r of 2. So 2 squared is 4, so that would put me at 4 pi, which would be about right here. Now we're going to do an r of 3. So that would give me, 9 pi, and that would put me right up here. And so I graph the curve, and I label it h equals 1. Again, the reason I'm labeling it is how would anyone know what it was unless you labeled it? We don't have any h's on there at all. All we have is r's and v's. So you need to label. Okay? Now let's work on the h equals 2 curve. So we're at this equation right here. I want an r of 1. That gives me 2 pi. So about right here. An r of 2. So 2 squared is 4. 4 times 2 is 8. So that gives me 8 pi. Right up here. It looks like an r of 3 will take me off the graph. It will. So I'm just going to stop there. And I'm going to draw this curve. And that's an h equals 2 curve. Okay? And you can put arrows on the end if you want. Or you don't have to. Okay? Let's work on the last one, the h equals 3 curve. So right here, if we put a 1 in for r, we get 3 pi. If we put a 2 in for r, let's see, 2 squared, 4. 4 times 3 is, yeah, we're off the grid now. We're at 12. So we're just going to kind of estimate maybe up here, and we can draw that curve. And this is an h equals 3 curve. And that's one technique of drawing a three-dimensional figure in 2 dimensions, is to hold one of the variables constant and graph multiple curves for it, for the function. Okay? Now let's look at the second technique. The second technique is when we are going to graph, we're going to hold volume constant, and we're going to graph h versus r. So this is h and this is r. Alright, so let's work on v equals 36 pi. Okay, so let's think what that means. What that means is I'm going to go back to my original equation, and I'm going to substitute a 36 pi in for volume. So I get 36 pi equals pi r squared h. And then what we want to do is solve for the easiest variable to solve for. I mean, it's easier to solve for h, so that's probably what I would do, and that's what I'm going to do. So h is 36 pi over pi r squared. We see those pi's cancel. So what I'm going to be working with is h equals 36 over r squared. Once I get a relationship between h and r, that's when I'm going to draw my t-chart. I'm actually going to do it out to the side just because of the way this is oriented, just be easier for me, with r and h. So I'm going to start with an r of 1, since an r of 0 doesn't make any sense. So let's go here. An r of 1 would give me 36h. That seems a bit big for my graph. I don't really want to graph up to 36. So let's keep going. With an r of 2, so 2 squared is 4. 36 divided by 4, that's 9. Okay, that's a good one. That's a good point. I'd like to graph that one. 3. So 36 divided by 3 squared. Let's see, 3 squared is 9. So 36 divided by 9 is 4. Okay, I just want to do one more. So 4 squared is 16. So 36 divided by 16 is 9/4. And I'll just kind of stop right there. Now, probably be a good idea for you to generate all of the points before you do your scale over here. I actually already have, done all the points, so I'm going to show you what scale that I put over here. So I did 6, 1 through 6 down here for r. So 1, 2, 3, 4, 5, 6. For h, I went up to 9. So 1, 3, 5, 7, and 9. Okay, so let's graph our first curve. Let's graph the v equals 36 pi curve. Alright, so at 1, r of 1, h is 36. It's way up there, so I'm not going to graph that one. At 2, r of 2, h is at 9, so that puts me a point right here. R of 3, h is 4, puts me right here. And then r of 4 gives me 9/4. What is that? 2 and a 4th. So at 4 we go somewhere in here. And then we just kind of draw the curve. And we're going to label it v equals 36 pi. So this is v equals 36 pi. Okay, we okay so far? Yes? All right, let's do the other one. Let's do the 72 pi one. It's the same process. I think y'all are okay with that. I'm going to go straight to h. I'm just going to write it underneath here so for room. So h for this one is going to be 72 over r squared. So we're going to do our points, r and h. We'll start with 1. That's 72, a little bit big for my graph. Start with 2, or 2 is next, so 2 squared is 4, so 72 divided by 4 is 18. That's still just a little bit big. Let's keep going. 3, 3 squared is 9, so 72 divided by 9 is 8. Okay, 4. 72 divided by 4 squared, or 16, is 9 halves. And I wanted another point, so I went out to 6 because I know 72 divided by 36 is 2. I just thought that would be easy. So I went out to 6 for another point. Okay, so let's go and graph those points. So 1 at 72, okay, those are really steep. I don't have that, but 3 at 8. 3 at 8 would be about right here. Then we have 4 at 9 halves. So around right here. Let's see, rounded here. And then 6 at 2. So something like that. And that's V equals 72 pi. Okay. These, yeah. 9 fourths, 9 halves. So I have this up a little. There we go. There we go. I fixed it, right? Okay. The last question, if H is held constant, what happens to V when R is doubled? Now, most of us are really good numerically. You could probably do this in your head. I encourage you to write it out algebraically, so that's what I'm going to do. So to do that, we want to double R, so 2RH. That's what we're wanting to do. So let's go through the formula and do that. So that would be pi, then 2R squared H, which would be, what, 4? So 4 pi R squared H. So we're going to compare this to our original formula to see what's happening. So if we compare this to the original formula, we can see that the volume, because they want to know what happens to the volume is going to be quadrupled. Right? So if we did that, the volume would be, the volume is quadrupled. Okay, how is that? Are we okay? All right.